All right. Welcome everyone to Polkadot Deep Dives. I'm Abhishek, and today we're kicking off a three-part series on frame benchmarking, and today is going to be about weight concepts. So buckle up. We hope you have fun, and let's get into it. So the objective is to give you a overview of what weight concepts are, how they're used for benchmarking, and in general, the purpose of these learning sessions, if you've been following us, is to promote learning and share knowledge about the frame palettes, substrate tooling, so that they can enable you to build better parachains and standalone chains. So the agenda for today is all about weights. We'll go on how they are used in the runtime, what are the data types involved, the traits involved, and we'll also share some demos with you and talk about weights version 2, also known as 2D weights. All right. So first off, blockchains are bounded systems. So what is meant by that? So a substrate, when you run a substrate node template, it comes with a 6-second target block time. That immediately tells you something. That tells you that we have limited computation, I/O, memory, and need network resources. As a block author, you need to run all the transactions. Then you need to make sure that they are running within memory bounds so that you don't have a out of memory error. Then you need to propagate it through your network so that other validators and other peers can get your block and then import it into the state. So all this needs to happen within a certain amount of time, and hence we need some kind of metric that would enforce such a bound. Weights are that weights are that instrument. So weights V1 are an instrument or measurement of on-chain compute time. So Substrate defines 1 unit of weight, which is something abstract, as 1 picosecond of computation. Now, picosecond is like 1 second has one followed by 12 zeros. So that many seconds of that much amount of units of weight. Now that's also defined against some reference hardware. So you can think about it like if I have a supercomputer and my 1 second of weight is different from somebody who's running a Pentium 4. So in that regard, weights are different. So it's always about in reference to something. What I'd like to point out here is that uh, going on with the theme of the previous slides, that weights are not the only metric for policing resource consumption. Uh, for example, you have memory usage, you have storage, you have the size of the blockchain, and you have other strategies. So you need to consider other strategies to deal with them. So, for example, how do you tackle the problem of memory constraints? So, if you look into the service file, you can see that you can specify the number of WASM heap pages that will start with your node. So we can start with just a gigabyte of WASM heap pages, and that's a hard constraint on your blockchain node. For blockchain size, we can limit that by implementing a per byte fee. So you can have a transaction, and you can have per byte fees for that. So that can help you limit the size that the blockchain is growing at, and we can also specify something called a maximum block length in the frame system configuration. So the you can see that this has nothing to do with weights. These are the other constraints. So as per our definition of weights, which was to control our execution time, or a metric rather, to measure our execution time, we are looking at other areas right here. Then finally we have storage. So if you'll notice this, that Polkadot, Kusama, and Substrate have this concept of existential deposit, which means that dust accounts are not allowed to take up storage. So you can set up a fee. Let's say you're building a pallet. You can set up a fee such that the user pays for the storage size that they are using. And yeah, so I urge you to look into other strategies, like whatever you can think of as separate from execution time, they need some other strategies to deal with. Moving on. So the wait vtime in code looks like just a simple wrapper over a U64. It's a struct with a ref time field and has a U64 which is measuring your weight, and there's just a simple function that returns that number. So weights v2 actually adds a second field, as Alex showed us earlier. They have added a proof size, so that for parachains you can track their storage consumption. Now, let's get into the configuration. How do you use weights in your runtime? So for that, we have this type called block weights, and block weights is just a getter over some this type here, which is frame system limits block weights. We'll be looking into more detail on how that's built right here. So it has three fields. So whatever is the maximum, or whatever is the weight configuration for your runtime, you put into this struct, and then this struct is, it's your main entry into the world of weights basically. So each block will have a base block weight consumption, which is like you have certain overheads. So you may have certain overheads regarding the network consumption. So we use that in base block right here. Max block will be the maximum or the target block time, which I have written here. So it's defined as the sum of max total from each dispatch class, and given that each this the sum may not exceed this, but there are cases where we have an extra reserve field that can bend this rule right here. And finally, we have the per class configuration, which will configure your weight characteristics for each dispatch class. Now, what we'll look into what dispatch classes are after this slide, but just know that there are three in total. There is your normal dispatch classes, which is just user initiated transactions. You can think about it like that. There is the operational dispatch class, which can be a simple palette. It's just identical to a normal palette call, but it has an extra annotation that helps your runtime understand that this has to be treated differently than, say, a normal execution. And finally, we have the mandatory class. So yeah, right here you can see these are the three dispatch classes, and there are some interesting points here. So for example, operational, you would use operational dispatch classes for something that is very essential to how your blockchain network functions. So it has some special rules, like it's exempt from paying length fees, so no transaction byte fee there, and it is given higher priority, so it can take up the entire block weight, or the entire block, if you will. So uh, that's there. And it also has, in most substrate node, it has a configuration for your reserve space. So let's say you have a operational extrinsic that doesn't fit in the max total that's defined by that dispatch class. You can extend that using reserve, which will allow for that operational dispatch to be included. And then we have mandatory, which is primarily used for inherent transactions. These are transactions that are injected by the validators, and thus they are like, also there are certain characteristics, like they have no upper limit. Like you can create an impossibly heavy block using just mandatory dispatches, but for that reason we need a different validation mechanism for that. So you can think about just the way inherents are verified by other validators. And if some malicious validators tries to build a very heavy block, you can slash them. All right. So here is the weight per class struct. again, this is another important struct that we saw in the previous slide. So you can see it's this per dispatch class is generic over weights per class, and this is actually used to configure each of the dispatch classes for your runtime. So that there is a block builder pattern. You configure it for you configure each dispatch class, and then that finally gets built into one block weight structure that you'll use in your runtime frame system configuration. All right, so let's look at a sample configuration right here. So you can see we define a struct. We say this is runtime block, and we define get block weights. So remember, that's coming from the requirement from frame system. And we say, okay, take for dispatch class normal. So for normal, give this base weight. So for extrinsics, you would like to have a base weight. So each extrinsic, regardless of its complexity, will come with a base weight that is consumed regardless. And this could include, uh, if you think about it, what is happening when you execute an extrinsic. So the caller's signature may get verified, and then you may have maybe you have a balance deduction, so the balance storage needs to be worked with. And I guess there was one more that I just can't recall, but maybe if we go through this, I'll talk about it. I guess it was the account nonce, if I'm not wrong. So, anyways, we configure weights max total as the normal weight. Now, this normal weight is actually it's almost always a ratio of the maximum normal weight of the maximum block weight. So let's say in a typical substrate node palette template, you'll see something like 75% of the maximum block weight as defined as the normal's dispatch class weight. So here you can say that, okay, this is normal weight. And for operational, you say it's maximum block weight. Now remember, this is just a sample configuration. There is no hard and fast rule that says that you have to do it this way. This is just one of the ways. This is one of the most common ways that you'll find it defined. And then we add a reserved weight. Now remember that max total field that I showed you in this previous slide, this max total thing. Now, this is an option. If you put this option as none, then there is no upper limit to what the maximum total can be. You basically wouldn't want that. So, right here, we have said that it's maximum block weight minus the normal weight. So, the normal weight is, whenever I say normal weight, think about the normal dispatch class weight. And then we say, okay, give it an average block initialization of 10%. So we are reserving 10% for on initialization handlers. And that's about it. This will give you a block weight struct that you can use in your frame system configuration. Now, here I have shown you how it's configured in the node template. So we define a 75% per bill struct right here, and we pass it to this function called with sensible defaults. So if you will just take a quick look at sensible defaults, it takes care of all those things. It takes care of defining what this dispatch class for operational will be. It takes care of what your base extrinsic weight will be. Everything. It gives you sensible defaults, as the name suggests. Only you have to provide this information, that what is your target block time, which is 2 seconds in this case, and your normal dispatch ratio, which is 75%. So it's 3/4 of 2 seconds. Now this is a typical block weights configuration that you'd see in a parachain. So if you're using Substrate parachain template, you might see something like this. So there's an additional field here that's set proof size, and that's stated to maximum POV size right here. So, and the weight is half a second. So that's those are it's some kind of calculation that's based with the relay chains 12. I'm not really sure about this, so don't quote me on that. But I guess it has something to do with async backing not implemented and the 12-second target block time of the relay chain. So it has something to do with that, but I'm not totally sure. But It's interesting to keep that in mind. Now, here you can see another way of defining 75%. You just take the maximum block weight and you multiply it by 3 and divide it by 4. So that's just 75% right here. And the same thing that we saw earlier, the runtime block weights configured for all. You can also specify the base extrinsic for all dispatch classes in one go, which you can see here. So it's just highlighting different ways of doing the same thing, really. Okay, now how are weights used in Substrate? So any Substrate developer knows how important weights are for their palettes. In fact, it's one of the first things that they write. So whenever you're writing a palette, you might hard code some value like this. So 1 million, which translates to about 1 microsecond of compute time. And this is actually important because if you don't specify what your palette is consuming, it can easily become an entry for a DOS attack. So also weights can be dynamic such that you can include some Rust code right here. So based on the input parameters that your dispatchable is receiving, you can write if some condition, then add 2 million to 1 million, or else do nothing, else add 0. So you can have, you can either hard code it or you can have it depend on the user inputs that are included in that palette call. Now this is just the upper limit for your dispatchable. At the end of the palette, you can actually return a reduced weight, or you can return a new computed weight, which can be less than this number, and that amount will be actually refunded back to the user. So refunds are also important to keep in mind here, that how are you actually determining this number? You are determining it by considering a few basic things. How heavy are your computations? Are you performing database reads? Are you performing database writes? And if you're using Substrate, you usually have access to a type like t db weight info, and that can actually help. Sorry, there's some sound there. Oh, so yeah, sorry about that. Uh, yeah, so you actually have access to some DB weights from the runtime itself that you can use to uh, um use for how many reads and writes you did. So you don't have to actually know the number; you just invoke that function. Another place that it's used heavily. So pallet hooks on initialize, they are run on every block. So uh, if you're designing a blockchain and you want some computation to run at every block start, you write it in on initialize, and then you return a weight up front. So that weight gets actually subtracted from your maximum block weight. So you actually get a small portion, you actually take away some portion of the weight just up front right there. And on runtime upgrade also, even on runtime upgrade returns you a weight that can tell you if how much space it will take in the block. But on finalize is special here in that it doesn't actually return a weight because it's actually run at the end of the block. And so it's actually discouraged to put heavy computations on finalize, as it can make your block too heavy to be imported by other peers. So just a quick recap of usages. There's storage operations, codec operations, searching and sorting. Say you are doing a binary search versus a linear search. That will affect how much weight you use. Calls to other palettes, if you're using other palettes through traits, you might want to consider what are the weights for that other call. Smart contracts, weight execution, obviously, and XCM. Again, when we talk about XCM, you have to understand that each chain that communicates with XCM is different. So they may have different configurations, different fee structures. So you need to actually buy execution from other chains in order to have your XCM message be executed. Now, how do you get a common interface for that? Waits provides you with that common interface. So you can purchase Wait, and whatever wait that you don't use gets transferred to the Sulpress wait register for the XCM executor. All right. Now, finally, fees. So we have been talking about this abstract notion of weights, which is just a number. But to have a real impact, it needs to be converted to fee. And for that, we have two traits in particular. One that I have shown here, that's weight to fee. So it's just a mapping between weights and the balance that's defined in your runtime. The other one that I think it's not shown here, I think I forgot to put in my slides, that's weight to fee polynomial that can actually give you a more fine grained structure to how you want to compute this weight to fee thing. And it actually returns a polynomial. So like this thing like a polynomial is n cube plus m square, and then you have various constants that multiply. So it can be a different function altogether. It may be a quadratic function. So yeah, that's something to keep in mind right there. Now we'll look at a sample implementation for weight to fee. So right here we have constant multiplier, which is generic over T and M. T is the balance, I believe, the balance type, and M is the multiplier. So this basically takes whatever weight you send it and it multiplies it with M get. So it just takes M and it multiplies it. Here you can see how it's being used. So U128 is being used for the balance type, and const U12810 is being used for the multiplier. So we need this const to generate the get implementation. You call that and you get the number 10 back. And so whenever you call this function, it is just multiplying it. You can see it's saturating mul. So you call it with 50 and it gives you back 500. So that's how you can control how much fees you're charging for and actually it's used by pallet transaction payment. So yeah.
Why they are important, what this migration has been important, and if you want to go more in deep, you know where you can go to find more information. So a bit of history here. This term, this was already around in 2019, where it was a bit different. It was called chromatic gas, and it was proposed for Gavin to Ethereum, and it was basically to have different gas metering for different resource consumptions. At the end, it was not implemented in Ethereum, but we brought that idea into the Polkadot ecosystem. So the main way to think about the weights v2 is that now we have like a multidimensional weights. At the beginning of Substrate, we only have like one-dimensional weights. We're only measuring the weights via the computational time, and now we have increased to this weight v2 to have like a multidimensional to be able to measure different things. This code that we have here, it was coined by Gavin when he was explaining which weight two in the Sub-Zero conference in November, and it's like the definition of weights v2 is a needed for automatic functions to be executed on parachain safely. The automatic function here means like some kind of migration that parachain wants to do, XCM calls or different schedules calls that we have, that the parachains have, that are going to be executed in the future. And the execute safely, that here means, so just to summarize how parachains and relay chain works in 10 seconds, the collectors of the parachain are generating the blocks, and then they are sending to the relay chain a proof of validity, which is a proof that the validators in the relay chain can check, and then they know if they can agree, and they know if the collector is cheating or not. So it's for the security of the parachain. So this change this migration to the weights v2, when we have had a new dimension to the weights, measuring the proof of validity that I just mentioned, improve the parachain security, because it can be like a problem if parachain has some kind of extrinsic that are very fast in the execution time, but it's improved, it's growing a lot into this proof of size validation proof. So that's why we address that with this weights v2. And also, it also makes the fee system more fair. So with a multi-dimensional weights, you are not only checking the execution time, you are checking, like, you are able to check much more the dimensions. So comparing the weights v1 to v2, so in the weights v1, it was very good for solo chains, because it's we have this way that checks measure the computational time used on based on some reference hardware. So this is the code that we have, is the type weight that is basically a U64 type. And now we have had a second weight into, so it's now a two-dimension weight, and we have add the weight of storage space used by the proof of validity. That is much better to measure that into the parachains. The migration was not easy at all, because it was changed the whole concept of weights. That again, this was how weights look like in the code, was basically a U64, and now we are converting into a struct weight that has a multidimensional and different variables. So it had like some intermediate steps that I want to mention. You probably don't have to. We don't have to worry about that anymore. This was in the version 9.29. Currently, we are in the version 9.40. But it's good for you to understand that it was not easy at all, and how was the process to migrate from the version 1 to the version 2. For here, we can see that the migration from 1 to 1.5 was to convert this U64 in a struct that allows us to have multidimensional weights, even though we still have like just one dimension. For the migration that had to migrate from the 28 to the 29, what they have to do was to go into the code and change, or in all the places, change where they have this weight to have the new structure of weights. That's why we provide this this regular expression that was like find and replace into the code. And how the final weights v2 looks like is like this. So we have the reference time that we already had in the v1, that is the computational time of extrinsic, plus this proof size, that is the second dimension. So now we have these 2D weights. And this proof size is, as I say again, the storage space used by the proof of validity. Not only that, so we only have two dimensions, but the whole point of this migration was to keep the system, to design the system to be ready to add more dimensions if we want in the future. So let's say that we want also to feed for the memory usage, or for the storage. So we can add a third dimension, or we can add a fourth dimension, more or less easy. Well, this is easier than this migration. Some interesting, well, some changes that have to do. So in the config, we'll change a bit the syntaxes. So now we use this bulk name weights and this new trait substrate weight. Then an interesting change is also the operation with weights. So before was like just unidimensional operations, and now we have like this multidimensional operation. So if we want to compare, if you have in the code, for the people that had to migrate in the code, so for example, the example that I put here is for a test that is checking that the weight is great, the weight of the info one, or the extrinsic one, is greater than the info 2 of the extrinsic 2. So to do that, now we need to use a new method that is all GT, that basically goes and compare not only one dimension, two dimensions, the rep time and the proof size. So we have like a lot of operations implemented into these struct weights that has like for different comparison or different arithmetic operations. Another one for to do the migrations was this function that we have here that was the conversion from an old weight to a new weight. The old weight here means this the 1.5 that we mentioned, where we already have the struct weight, but we only have one dimension, the ref time. So in this migration, basically what it does is take the first element of the old struct, the ref time, and add it a default value for the proof size using this from parts method. From parts is basically a constructor when we can create a new kind of weight. And again, if in the future is we add a third dimension, here in the constructor, basically we are gonna just add a third parameter. And another example of code that some people had to do in that migration was to go to all the weights that were specified and modify to manually to be able to use the new type of weights using this constructor from part. So this example is for the extrinsic do something. The extrinsic do something is for in the palette is a palette template that we have in the node template in the Substrate repository. And basically here we only have the 10,000 hard coded, so now we have converted 10,000 for the new weights using this from parts method. These two things are highlighted because we can skip it now. There is already a pull request where the developers are trying to get rid of all this migration from old weights to new weights, and then this second part, this do something function that is already highlighted, this part, that also should be skipped because now we can calculate the weights in a better way that we're gonna see now. We don't have to hard code it the weights like it was in this example. But I think it's interesting just for you to know how was some steps that had to be done into the migration. So to calculate now the weights, that's to calculate weights we use benchmarking. I'm not gonna talk a lot about benchmarking because the next learning session next Friday and the next Friday are gonna be specifically about benchmarking. So that's gonna be useful to understand it. But basically, benchmarking is a tool to calculate the weights, to have the accurate weights, basically checking the worst case scenarios that we can have and calculate estimating the weights. So in the version 9.35, just two versions behind the one that we are now, it was like this was updated this frame benchmark CLI that is used to estimate the weights. So now the proof of validity side, this new weight is added into the estimation. So we don't have to do it hard coded. We can use this tool. Also, it is recommendable to use this tool, this frame benchmarking CLI. And what people had to do here, the people that had nodes already or some palettes, what they had to do here was re-benchmark all the palettes to generate the new weight using this tool. And also at the same time, so ensure that the proof size will not overflow the block limit. So check that all the weights make sense and not overflow the limit that has in the block. And this is a pull request that is open into the GitHub repository of Substrate because the weights v2 migration is still ongoing. It's still not considered totally closed. Here we have like a list of things that I already told, like for example, all the implementation of different comparison methods, change from this remove rectangle weights means the change from the version 1.5 to the version 2, etc., etc. And at the end, we see that there's still two pending that are related to the max proof size and the proof of validity size. What is the max proof size? So the max proof size for this weight, for the solo chain, so for the substrate-based chains that doesn't require to submit proof of validation blocks to the relay chain, this is the maximum U64 max. It is with 64 max because it is the maximum in this field. Proof size is a U64, so it's the maximum because we are actually not using proof of validity. And for parachains is a bit lower because for parachains this comes from the relay chain. And the max from the relay chain, this is a chunk of code that comes from the Polkadot repository itself, this is the max proof size that you can have in your weights. And yeah, finally, so I've been recollecting some issues that people have been encountering where they were doing this migration with weights v2, mainly from a stack exchange. The first one is related with Ink smart contracts. So some people were complaining that when they were using Polkadot.js to deploy an Ink smart contract, they were getting an error related to the gas consumption. And this was because the Polkadot.js UI doesn't support the new type of weights yet. The solution to that, if you want to deploy a smart contract, for now you can use this contract UI. That is a platform, a website that the Ink team developed in order to to deploy smart contracts and have a workaround to work with weights v2. If you are using a Polkadot JavaScript library and you want to do it manually, that's a bit more complex, but you can add this weights v2 type manually in the code. And the good thing is just to fix Polkadot.js to support this Waze v2. And I've seen like a couple of days ago that there's already a PR that has been accepted. So probably it's gonna be live soon in Polkadot.js UI. That error is not gonna be anymore. But if you find this error, just you to know what's the different solution. And another error that some people found is some kind of error when calculating new weights. There was proof skipped error message there, and this indicates that the worst case scenario for the proof size limit was not able to couldn't be estimated with the CLI tool. The solution to this, the best practice when you are developing Substrate frame is to have all the storage bounded, so to have a limit in all the storage. So the solution to this is to try to have all your storage bounded. So for example, if you have a vector can grow unlimited, can grow without your control. So have this kind of control. So one of the options is to migrate from the vector to bounded vector. That is basically a vector that has a limit of elements. That's not easy to do all the times in the migration. So another is to change the mode of when you are calculating these new weights to be more flexible, to say that way. The problem with that is that it cannot reflect the worst case scenario, and we will see in the demo that Daniel is gonna do what happens when you underestimate weights. What problem can happen with that? And another problem I've seen around Stack Exchange that can apply is like we're doing this RPC method call that is called payment query fee info. That is to more or less estimate the fees that you're gonna spend. It was failing. That was because you had like an old version and that was fixed in the version 9.32. So you experiment this issue, just update to the version 9.32 because it's already fixed to work with this new type of weights. And that's it. Yeah, gonna pass to Daniel to do the demo, or to Abhishek if he's already back to be able to talk again about the main concept of weights.
Okay, so I'm Daniel Bigos. Welcome everyone on the demo. After my demo, we will have Abhishek, who will, give some more overview about weights. But yeah, about the demo. This is not the regular demo as we had previously. I mean, the demo that I'm going to show is more about key lessons that you need to take into consideration while creating the runtime. But at first, let's provide some overview. So why weights matter for builders, for runtime builders? So at first, weights are used in extrinsic. I mean, they tell people how many resources will be used by extrinsic. It also helps Substrate to calculate how many extrinsic can be taken to the block production. Besides extrinsic that are really important to builders and have some impact on building blocks, I mean filling the blocks, we have also hooks. So as it was presented some time ago, every palette has a list of possible hooks to be implemented, and that hooks during some of the block execution time are triggered with every palette inside the runtime. But while talking about hooks that matters for building blocks and hooks that take some of the weights, there are three. So at first we have onInitialize hook. That hook is triggered with every block when every block is getting created at the very beginning of the block creation process. So for that hook, we need to provide how many weight will be used for that hook. Also, we have on runtime upgrade hook. So that hook is triggered when we have runtime upgrade. And also for that hook, we need to for that hook, we need to also tell Substrate how many weight will be used. And the last hook that is triggered and matters with weights is on idle. So this is the hook that is triggered after extrinsic are applied, and there is one condition for that hook to be triggered. So imagine we have block almost filled with weight. So for executing that hook, we need to have enough weight. So when we have almost packed block and we have no weight, that hook is not triggered. In other case, that hook is triggered. Okay, so having provided some introduction to hooks and extrinsic, let's talk about the common mistakes that I have faced while checking some of palettes runtimes. This is the key takeaway of that demo, to be aware what can happen when builders do some of the mistakes. So the first mistake is usage of unbounded vectors. That's the main point. But also, I have seen a lot of troubles also with bounded vectors. So imagine a situation that we have an extrinsic that does an operation on each element of the vector provided as a parameter to that extrinsic. In that mistakes that I've seen, the weights weren't coupled, weren't adjusted to the size of the vector, but they were adjusted to the size, for example, of 3 elements. But in a situation that we have very long vector with multiple elements, and we need to apply some calculations on each element, we can exceed the block time, and we will see what will it cause. And the second problem with the extrinsic runtime implementation that I've seen is a way of uncovering some execution path within extrinsic. In other words, imagine a situation that you have an extrinsic and you have some if conditions, and based on that conditions, you have different execution paths. And for example, we have an extrinsic with weight that is adjusted to shorter execution path, but the longer execution path is not covered. And based on wrong weight, that extrinsic can exceed the block weight. The last part are hooks, mistakes that are kinda matched with hooks. So imagine we do some operations at the very beginning of each block or at the end of the block while we have some weight left. So imagine we have very big state. for example, a list of identities stored in our palette state. And on that hook, we need to iterate over every identity that we have stored in our state and do some logic. So in a case that we underestimate the weight for that hook, we can also exceed the block weight even if on initialized hook. So those are the 3 common mistakes that I have faced while reviewing multiple runtimes. And to be honest, this is not only about talking, but this is a situation that happened in the past. I mean, the situation called Shanghai attack. It was denial of service attack on Ethereum that took place during the second DEFCON. That was in Shanghai in 2016, as I remember. Basically, what happened at that time was sending multiple transactions that were using one Ethereum instruction that was underestimated in a sense of fees. So it caused that the network wasn't processing almost no processing block during that time, and there were many delays. So that attack worked. I mean, attackers were successful while providing data. So this is a serious problem. So I hope you will not do that mistakes that I have described, because that attack can happen to you. Okay, after the introduction, we can start trying to hack a substrate node. Okay, so I have a parachain running. That parachain have 5 collators, some validators for the relay chain. And for hacking, I have prepared the dedicated palette. So this is an extrinsic that I trigger extensive computations. And the only one parameter for that extrinsic is a number of iterations, a number of repetitions that the computation will be done. I will show what kind of computations it's going to be, but let's check what will happen with 1 million of iterations with the same extensive computation. With 1 million, it should fit into a block. I should get an event that everything is fine, everything works well. Yeah, we have an event, blocks are still creating. So we can assume that for that parameter, everything is going fine. But let's check what will happen when I will double the amount of iterations. So my previous extrinsic was okay for the block weight. So let's check what will happen with doubled amount of iterations. Okay, so I put 2 millions. And let's go into code for a moment. So this is the extrinsic that I have prepared. Oh, this part of code can be interesting to you. So in that part of code, besides specifying the weight for the extrinsic, I have also specified the dispatch class for the extrinsic. The dispatch class will be covered by Abhishek when he will be back. And for that extrinsic, the dispatch class is set to normal. And this is the default dispatch class of every user extrinsic. The third parameter passed is enum of pay. And this parameter tells the runtime if user needs to pay for execution of that extrinsic. But what does the extrinsic do? So it triggers an event and triggers a long-running task. And what is long-running task? Okay, so long-running task is multiple iterations doing the same stuff, and it's calculation of just a factorial of 30. So basically, this is quite expensive, computation. So let's see what will happen on Substrate runtime if blocks are produced or no. So as you can see, the parachain has stopped. Last block was produced 2 minutes ago. Let's check on another validator of the same parachain. Last block was produced 2 minutes ago. Let's check details of that parachain on our relay chain. The same information that last block was done 2 minutes ago. So the summary of that is when we exceed the block weight in extrinsic, our parachain will stop. So this is the first mistake that you can do in your runtime, and you need to avoid this. The second mistake, I need to restart my my setup, but let's go to the extrinsic. So what I'm gonna do now is that I will set the flag, will put the flag to the storage, and then while reading that flag on initialize hook, I will trigger the same long-running computations that exceeded the block weight in a previous example. So this is the extrinsic to set the flag. This is only one write to storage. And this is a hook. So we read from storage and the flag, and if the flag is set to true, we trigger the long-running task that exceeded the block time. So let's go to our UI. I need to refresh everything, and I hope everything is producing block after initialization. Okay. Yes, I'm using ZombieNet to run my parachain, and that parachain is based on the Cumulus parachain template. Okay, so we are back, and the whole parachain is set, is fresh. So let's set that flag to hack our parachain. So when I submit that extrinsic, that flag will be saved to the storage, that block will be created, but at the very beginning on the next block, we should stop our chain in that case. Let's see. Okay, so our flag has been added, and the same should happen with our parachain. So yeah, as you can see, we are over 12 seconds, but let's wait to confirm that I am right. For a moment, we can go back to my implementation, because there is something that I want to point out to every builder, and this is in factorial function. So whenever you create or even do some extensive computation, mathematical computation, use safe math operations. So for example, in that factorial, I can easily exceed overflow unsigned int. And for that operation, I have used checked operation. So remember also about that kind of mistakes. It was great to have you all. Thank you. See you in the next week.
Thanks, guys.
Bye.
Bye
Thank you.
bye.
Cheers, byes.